Hello everyone. So again, welcome back to our latest lecture session. So let's have our customary review, I guess, for a few minutes about what we have been up to in the last couple of sessions, and then continue with where we left off, right? So I guess we were looking at reaction feasibility or with respect to equilibrium, right? So we are discussing redox reactions, yes, and we looked at the different terms and so on, electron acceptors, donors and so on, and then we moved on to discussing kinetics. We were done with that, and we started discussing about equilibrium, right? And I guess we are just going to quickly recap what we have been discussing with respect to equilibrium. So again, as we mentioned or discussed, right, most of these redox processes, though they are feasible, right, they will not go through because of the kinetics being way too slow, right? So in general, what is the norm? Redox disequilibrium is the norm, right? That's something that we have understood from our last couple of sessions. But obviously looking at equilibrium will help us in understanding, let's say, is the reaction feasible or not feasible, right? So in that context, we looked at two approaches, and one of the approaches was looking at Q by K, right? So how did we get here? So for one half reaction, we can calculate K1, or we not calculate, pardon me, we can obtain the relevant K1, right, equilibrium coefficient. For the second half reaction, get the relevant equilibrium coefficient again, right? And then you are going to sum up 1 and 2, right, after modifying either reaction 1 or reaction 2, so that you will equate the number of electrons being transferred, right? And then we saw how we can come up with our particular K for the overall reaction, right? For the overall reaction, we looked at how to calculate that particular equilibrium coefficient, right? And obviously again the key is that we need to see to it that the number of electrons being transferred would be the same in both this reduction and oxidation process or the half reactions, right? So again we did that, and then you can calculate Q, right, based on the relevant concentrations that you have in your particular system. So Q will tell you an idea about what's the present scenario. K will give you an obvious idea about what's going to be the system, or how is it going to be at equilibrium, right? So when you look at Q by K, and obviously if Q by K is less than 1, it means that the reaction is feasible. Equal to K, it means it's at equilibrium, and greater than K, it's not feasible, right? So that's something that we looked at in some of the previous classes, and that's something that obviously we looked at from the point of view of the redox process. And then we started looking at a new approach, right, or a different approach, something that we haven't looked at yet, the reduction potential or the PE, right? So in this context, we first obviously looked at how to get at that PE. So how did we get that? We wrote down the equilibrium coefficient for a particular equation, and this is the particular example I believe we looked at, right? We looked at the particular equilibrium coefficient, right? Stoichiometry of the products, right, to their coefficients by activities of the relevant what is it now, the relevant reactants, right? We got that done, and then we plugged it in, transformed the equation such that more or less we end up with PE equal to PE naught minus 1 by n log Q dash, right? So again let us try to refresh what it is that we need to understand with respect to each of these terms here. So PE is your reduction potential, which is what we are going to consider with respect to determining our redox reactions feasibility, right? And P naught, if we look at how we derived that, it was equal to 1 by n log K, right? So it gives you an idea about the system at equilibrium, obviously, right? So again Q dash is nothing but, I guess, Q multiplied by the electrons raised to the stoichiometry of that particular or the number of electrons being transferred, right? And again what is n? N is the number of electrons being transferred, which in this example obviously would be 3, right? So Q dash, let me just try to write down Q dash here for this particular example. So Q dash is going to be equal to activity of Cr3 plus, which we usually approximate by concentration, right, by CrO4 2 minus, right. So we are not going to have the term electron term here, divided by H plus to the power of 8. So that is Q dash here, and we know what PE dash is, and from that we can obviously calculate PE, right. So again now we need to understand, I guess this is where we were at last time. So now we need to understand the significance of each of these variables that we have looked at now, right. So obviously Q dash gives you an idea about the current state of the system, right, Q dash, yes. So we have PE equal to P naught minus 1 by n log Q dash, right. So Q dash obviously gives you an idea about the current state of your particular system, and P naught, right, obviously gives you an idea about the equilibrium, right. So in this context we need to understand what does it mean when there is a high value of P naught or low value or such, right. So again for that we need to understand what does K tell us or give us an idea about. As you see, K is nothing but the activity of these what is it now, products by activity of the reactants, right. Obviously product of the activity of the products divided by the activity of the or product of the activity of the reactants, right. So raised to their stoichiometric coefficients. So obviously this is our equilibrium coefficient. So when is this particular equilibrium coefficient going to be high? When is it going to be high? Obviously when the products, the activity or the concentration of the products is going to be high, right. And if you remember, the way we wrote down the relevant equation or the half reaction was oxidized form of the compound plus electrons, right, or taking in the electrons goes to its reduced form, right. A in its oxidized form, right, accepts electron and then transforms to it to its reduced form, right, and that is what we see here, I guess. Chromium in its oxidation state number 6, I guess, right, O4 2 minus, yeah, 6 to 3, right, it is taking in electrons. So it is in 6 oxidation state taking in 3 electrons, and thus the oxidation state of chromium is reducing to 3. So that is what you see here, right. So again generic form is nothing but A oxidized plus the number of electrons being accepted to the reduced form of the relevant compound, right. So obviously here what does it mean now? If I write it down for this particular equation, so K, let us say, will give me an idea about what now? A activity of this particular reduced form, let us say, by activity of this oxidized form, right, in general, yes. So obviously what does it mean to have a greater K? That means that the reduced form of this particular compound would predominate, right, or that the reaction or would want to go in this particular forward direction. So that is what a higher value of K would mean, right, or that the reduced form would predominate. So again higher value of K more or less, as you know, translates to a higher value of PE naught value. So for example from your standard tables, if you look at the relevant PE naught values, let us say of particular half reactions, and you see that the relevant PE naught value is high, what does that mean? That it means that for that particular system at what you say now, the reduced form would predominate at equilibrium, or this particular forward reaction as written is going to predominate. And in which way do we write these standard half reactions? I guess as reduction, right. The oxidized compound is accepting the electrons and transforming into the reduced form. So thus obviously we can understand that this is a reduction process, right. And also keep in mind that this is the way how the standard half reactions are written, and obviously if you want to look at oxidation you need to transform the or swap the reaction, yes. So again so whenever we have P naught value to be high, that means this forward reaction or the reduction is what do we say, favorable, I guess, right. So that is what we understand from PE naught, I guess, right. So now let us move on to PE now, right. How do I understand PE in relation to what I have here as in PE naught, let us say, right. So for example what we usually look at is PE minus PE naught, right. So if I look at this particular set of variables, let us say, what is it that I can understand? There are two cases obviously, one when it is low and one when it is high, right. And what is PE again? As we know, it is minus log activity of electron, right, and that too in the current state more or less, right. PE is the negative log activity of the electron. So it is obviously similar to pH, right. pH is the negative log or logarithm of the H plus or the activity of H plus, right. So obviously here let us say, what does a low PE value mean? Similar to a low pH value, what do we say, meaning that higher H plus concentration, again it is negative log, right, that is something that is logical. So again low PE value, right, a low PE value would mean a higher activity of your particular electrons, let's say, if it existed in solution. Again, as we discussed, electrons would not exist in solution, right? Both these oxidation and redox process or reduction process would go in conjunction. You will never have electron pools, right? So again, but if for this theoretical half reaction, let's say, if the Pe is less, obviously from this particular equation you can see that the activity of the electron will be higher. So obviously if you look at this equation again, if the concentration or activity of the electron is higher, right, what does that mean now? Then again the forward reaction would be much more favorable, and that the half reaction would want to proceed in the forward direction, right. So that is what it transforms into, as in when Pe then compared to Pe naught is low, what does that mean? It means that reducing conditions prevail, right. So again, where is this from? Low Pe means more or less higher concentration of or activities of your electron. As we look at from this equation 2, it shows you that the reduced form would predominate. When would that be? Obviously when reducing conditions prevail. Reducing conditions as in you have electrons, right. So if you have electrons, obviously the reducing conditions will prevail, right. And same case here. So relative to P naught, we are looking at P, and if that value is much lower, right, what does that mean? P is pretty low, and that means obviously the reducing conditions prevail, right. So that is what you need to understand. So obviously if Pe minus P naught is high, what does that mean? So relative to that, so relative to equilibrium conditions, you see that oxidizing conditions will prevail. So you have a high value of Pe minus P naught. So P naught gives you an idea about the system at equilibrium, right. So obviously higher value of Pe minus P naught, right, let us say, right. So is going to obviously mean that you are going to have, what do we say, oxidizing conditions prevailing, or a dearth of your electrons here, that is a way to understand, I guess. So obviously here we have a graph, but before we go further, let us say, or try to understand that particular graph, we should also be able to visualize what it is that we are trying to say, right. So let us plug this in forms of what we know. So let us look at this equation again here, that is the generic equation we have here for now. So oxidized form plus the electrons, right, go to the reduced form, right. So what is this similar to, let us say, right, it is similar to, let us say, my base plus H plus, right, going to, or my acid, right. So in this redox process, when we have the acceptance of the electron leading to formation of the reduced form of the compound, it is analogous, right, or it is similar to base accepting the H plus, right, and then the acid being formed, yes. So and from this particular equation 2, we can also try to draw what do we say, comparisons between P naught and let us say the pKa values, let us say, right. And let us try to understand from the graph that we have in the next couple of slides. So let us try to understand this system in terms of these acid base reactions that we looked at, and let us try to draw that pH pKa graph that we have always looked at. So this is the concentration on the y axis, and let us say pH on the x axis, right. And what did we have? We had our protonated form HA, right, and here we have our deprotonated form, or A minus, right. This is for obviously the reaction where HA goes to A minus plus what is it now, H plus, right. And again, or in the way that we want to understand now, H plus A minus goes to HA, and this particular point when both the concentrations are equal is pKa, right. So what I am trying to understand, or try to help the relevant people visualize, is that, so here let us say, like, this is the compound without the proton, and this is the compound with the proton. Similar to that, what we are saying is the equation that we have, electrons being accepted by the compound without the electrons and compound with the electrons, right. So here A oxidized is the compound without the electrons, A reduced is the compound with the electrons, right, or after the acceptance of the electrons. So, we are trying to draw an analogy between these two acid base and redox process, but it helps you in understanding this relevant figure that we have here again, right. So, in this context again, we, if you remember, we had our pKa, right, acid dissociation constant, at least for this particular reaction, right. So, again the concept is similar here, right. So, here again we have concentration on the y axis, and on the x axis we have Pe instead of pH, obviously, right. For our acid base cases we had pH. So, I guess this figure is a bit more detailed. So, for now I guess this particular point is going to be Pe naught now, right. So, we are going to look at when this particular set of variable is going to be worthwhile, but for now we are going to consider this point to be at P naught. So, again keep in mind that this is similar to your pKa, I guess, right, for your particular case of acid base, right. So, again you have concentrations here Pe, and let us say P naught is the case when obviously both these compounds would be at the same concentration, right. So, let us try to understand that too. So, we have Pe is equal to Pe naught minus 1 by n log q dash, right, and what is q dash for this particular reaction? A reduced form, right, by A oxidized form, right. And if you remember again, this I guess is similar to pH is equal to pKa, right, minus log activity of HA by activity of A minus. Again I guess it is this is the Henderson-Hasselbalch equation that we looked at with respect to our acid base process, right. This was the Henderson-Hasselbalch equation, or a slight modification of it, right. So, again look at the analogies here, I guess, right. So, A reduced as in compound with the electron by the compound without the electron, and here compound with the proton divided by the compound without the proton, right. So, that is what we have here, and you see the analogies, and similar to this here, let us say it is we have here the reduced form or with the electron, right, and this is the particular profile for that, right. And here we have oxidized form or without the electron, and obviously this is the profile for the oxidized form. And you see that, what do you see now, when Pe is less than Pe naught, right, or in this region, right, when Pe, this is Pe x axis and Pe is less than Pe naught, this is my Pe naught, right. So, in this particular region, what do I see, which form obviously predominates? It is the reduced form, and obviously why is that again? Pe less than P naught means high electron activities, right, and thus obviously reduced species would predominate, right. So, again this is obviously visualization of the equations that we looked at earlier, right, or the explanations we looked at earlier. We looked at a case where I guess we had low values of Pe minus P naught, and that is what we are trying to understand or look at it here, right. So, what do we have here? So, if you look at this particular area, what is this particular area now? Obviously, when Pe minus P naught values are low or P is less than P naught, right. So, this is the P naught case, the P naught here, right. So, that is what you see again, right, when P minus P naught is low or P is less than P naught, let us say, obviously we have higher concentrations of or activities of these electrons that you would expect, right, these are theoretical values. So, obviously when you have higher concentrations, what does it mean? A oxidized plus an electron goes to A reduced, right. So, obviously when you have higher concentrations of these electrons, what does it mean? You will have higher concentrations of the reduced forms, right. So, that is what you see here, as in A reduced form predominates when Pe is less than Pe naught, right. So, that is obviously the take home message here, and obviously similarly I guess in that region where we have Pe is greater than Pe naught, right, what do you see here, or when Pe minus P naught values are high, what do you see obviously, right, you see that A oxidized form would predominate, yes. So, obviously when would both these A reduced activity would be equal to the activity of A oxidized, right. So, if we look at that, we have the equation to be P equal to P naught minus 1 by n log what is it now, A reduced by A oxidized, right. So, obviously, when will these two variables be the same? When Pe is equal to Pe naught, right. Then what do you see? You see that activity of this particular reduced form of the compound will be equal to the activity of the oxidized form of the compound, right, and obviously that is what you see in here in the graph. So, at P naught or at this particular point, what do you see? You see that activity of the reduced form is equal to activity of the oxidized form, right. And again, this is similar to our pH and pKa graph, right. If this were the acid base relevant graph, what would be? Here you would have HA or the protonated form, here you would have the deprotonated form, right. So, similarly here we have A reduced form means with the electrons, and here you would have A oxidized form meaning without the electrons, right. So, that is how you can help understand the system, I guess, right. So, this was the case when we had a simple example of what do we say, oxidized and electrons being accepted and the reduced form, I guess, right, being formed. So, now we are going to look at a couple of examples, I believe. So, for this case, let us try to understand how to write the relevant aspects, right. So, obviously, Pe will be equal to Pe naught minus 1 by n. N is the number of electrons being transferred, here it is only 1. So, I am going to write minus 1 into log q dash, right. So, activity of Fe2 plus, which is reduced form, by activity of Fe3 plus, yes. So, that is what you see here again, Pe is equal to Pe naught here, pardon me, right, Pe naught minus log activity of Fe2 plus by activity of Fe3 plus, right. And obviously, again, as we looked at it from the graph, when are the concentrations of the reduced form and the oxidized form going to be equal, right. Obviously, you see that is going to be the case when Pe is equal to Pe naught, right. So, I think that is something that is obvious to understand. So, again, this is the simplest case when you have only the oxidized form, right, taking in or accepting electrons, and the reduced form being formed, I guess, right. And obviously, this is your oxidized form, right, oxidized, it is taking in electrons and it is forming the reduced form, right. Obviously, oxidation state here is 3, and because it is accepting 1 electron, it is reducing to 2, right. I think that is pretty simple to visualize. So, let us look at one other or a couple more examples when we also have other compounds present here, primarily H plus, right. I believe the next particular example would be the one with respect to having H plus. So, we are going to look at a particular example or couple of examples, obviously, when we are going to have other compounds, primarily let us say H plus, I guess. So, I guess here is one example that I believe we have always looked at or considered until now, right. We have the reduction of chromium from oxidation state 6 to 3, right. But unlike the earlier case where we had just the oxidized form and electrons being accepted and forming the reduced form, right, we also have, what do we say, H plus here too, right. So, N is the number of moles of the electron, and NH or the stoichiometric coefficient, NH is the stoichiometric coefficient of H plus here, right. So, here let us say how we can modify the equation for our particular case. So, let us write it down in the way that we know. So, we know that Pe is equal to Pe naught, right, minus 1 by n log of q dash. And what is q dash in this particular case? Obviously, it is activity of Cr3 plus by activity into activity of water dilute solutions, that is equal to 1, and activity of CrO4 2 minus, right. And electrons, we already considered that here, obviously this is q dash, we are not going to have the electrons term here, into H plus to the power of 8, right. And 1 by n, this n should now have been 3, right. So, I am going to say 1 by 3. So, again let us see how this is going to transform into Pe equal to Pe naught minus and I am now going to bring this term out, right. So, what is that going to be equal to now? So, that is going to be equal to minus H, right, minus pH minus log H plus, right, which is pH, and let us say because it is in denominator again, minus pH, and it is going to be 8 here, right. So, it is going to be 8 by 3, right, minus 1 by 3 log Cr3 plus by CrO4 2 minus, right. So, if I want to write the generic term for this, what is this going to be? Obviously, Pe is equal to Pe naught minus NH by N into pH minus 1 by N log activity of the reduced form by activity of the oxidized form. And the reason we express H plus outside this set of what do we say variables is that usually let us say when we calculate Pe, P naught values or 1 by n log k values are remarkably or not remarkably I guess are significant compared to this q dash or log q dash values, right. But let us say pH though will have a considerable role to play, yes. So, again what I guess I was trying to say is that we had Pe equal to P naught, right, minus 1 by n log q dash, right. In general though we have two variables here, P naught value will be relatively high compared to this particular set of variables, right. But let us say though when we have H plus involved though, that will have a considerable what do we say effect on your Pe, right, or pH will have a considerable effect on your reduction potential, that is what we are trying to say here. So, for that particular reason we try to express that outside this particular q dash term and then come up with something called let us say P E naught W, right, which is nothing but P naught minus NH by N times pH. So, in the standard tables many times you will see this particular variable expressed, not just P naught. So, obviously when you see that, that means they are talking about P naught minus NH by N pH and usually at pH 7, right. So, that helps you understand the system better rather than having H plus inside the set of variable q dash, right. So, that is one particular case, pardon me. So, in that context let us look at the relevant what do we say relevant figure with respect to concentration of these reduced and oxide forms and the Pe. So, again here unlike looking at Pe minus Pe naught which was the case earlier, we are going to now look at Pe minus P naught minus NH by N times pH, right. So, this is what we are going to look at. So, the relevant relative term or variable we are going to refer to I guess or the reference term is going to be equal to P naught minus NH by N times pH, right. So, and that is what we have here. So, earlier if you remember for that particular equation which was just A reduced plus or A oxidized plus N electrons goes to A reduced form, we did not have this particular P naught minus NH by N pH, we just had P naught. But now when we also have A oxidized plus NH H plus, right, plus N electrons goes to A reduced forms, right. So, obviously here the reference term is P naught minus NH by N pH, right. So, again it is similar to that particular figure that we visualized earlier. When Pe is less than this particular set of variable, obviously what would predominate now or what would that mean now. So, Pe greater than or less than this particular reference means that Pe is very low. Pe very low means high activity of electrons, right. That is what it means, high activity of electrons. So, obviously if electron activity is high, that would promote formation of your reduced species, right. So, that obviously means A reduced form would predominate or obviously the compound without with the electron, right. So, obviously on this particular side as in greater than this particular reference, what do we see? We see that the oxidized form would predominate. Why is that? Because low Pe values, right, not low Pe, high Pe values leading to low activities of your particular electron. Low activity of your electron means oxidized species would predominate compared to your equilibrium, right, and thus obviously your oxidized form or the compound without the electron would predominate, right. So, again when would your particular what do we say concentrations of these reduced and oxidized species be similar or the same, pardon me, it is going to be when Pe equal to this particular reference P naught minus NH by N pH, right. So, earlier when were they equal? Earlier as in for this simple case when Pe was equal to Pe naught, right. In this case obviously now we have a new set of reference, that would be the case when Pe equal to P naught minus NH by N pH then we would have the activity of the reduced form equal to the activity of the oxidized form, right. So, that is one particular set of case, I guess, right. So, now we will move on to, I guess, another case when we have not just the oxidized form and the reduced form, but a few other elements, I guess, right. Let us try to understand that. So, here we have, let us say what else do we have? We have the oxidized form here, right, A oxidized plus NH times H plus N times electrons goes to the A reduced form, right, plus here we also have the other elements, let us say in this case 3Cl minus, right. So, obviously here we need to again try to understand the system. So, we have Pe equal to Pe naught, right, minus NH by N, NH is 1 by N is 2 times pH, right, minus log Q dash. What was log, or what is log Q dash? It is C2H Cl3, right, into Cl minus activity raised to the power of 3 divided by C2 Cl3 and its activity here, right. So, we will just look at the simple case when our concentrations of C2 Cl3 would be equal to the concentrations of C2H Cl3, right. So, obviously when would that be the case, right. Let us try to take this Cl minus term outside, right. So, it is going to be equal to P equal to P naught minus 1 by 2 pH, right, and we are going to have minus 3 log Cl minus activity, right, minus log of the reduced form by the oxidized form, right. And obviously when will this particular equation be valid? When Pe is equal to this set of variables, yes. So, again just for our purposes understanding, we start with the basic example when we had just the oxidized form accepting a few electrons and transforming into the reduced form, and then we also looked at the case where we also have H plus, and obviously now we are looking at a bit more complex what we say system, I guess, or the half reaction, a bit more complex half reaction, right. But again the objective here is to be able to understand the basic equation and how you need to transform it or visualize it, so that you can look at the relevant variables and understand the underlying aspects. And primarily obviously what do we understand here? When Pe is low or lower than your particular reference, which is P naught or P naught minus NH by N into pH, right. What does that mean? That means your particular activity of electrons is high, right. Let us look at that equation here, right. So, we will just summarize, right, for today, and that means high activity of electrons, meaning your reduced species concentration is going to be higher. That means A reduced form is going to predominate when P is less than your particular reference, and that is what we see here. And obviously the inverse of it, when Pe is greater, right, or greater than your particular reference, what does that mean? Low activities of your particular electron, and that would correspond to lower concentrations of your particular reduced species or higher concentrations of your oxidized species, meaning oxidizing conditions predominate, right. So, thus A oxidized form would predominate. And again, how can you understand this? I guess it is similar to your pH and pKa graph that you looked at, let us say, right. And similarly I guess A reduced form would correspond to the acid which is the compound with the proton, right, and A oxidized form, meaning the compound without the electron, would be similar to the compound without the proton or A minus, right. I guess with that I will end today's session, and we are now going to look at, let us say, how can I look at two half reactions, let us say, and the relevant P1 or Pe values or the reduction potential values, and then be able to understand which particular compound will then act as the oxidizing agent, right, and which one will then act as a reducing agent, right. Anyway, with that I guess I will end today's session, and thank you.